force on the wire, because the current and the magnetic field are perpendicular to each other, it's simply I, the current, L, the length of the rod, B. Now the current is the induced EMF over the resistance, and the induced EMF is simply VLB or LBB, and therefore the force on the wire's magnitude is given by this expression. Okay, LB squared V divided by R. Now we know that the power, okay, is the current squared times the resistance. All right, they're giving you the power dissipated, which is 50 millivolts or milliwatts or 0.05 watts. Therefore, the resistance is 5 ohms, not 5 milliohms. Where did you get 5 milliohms? Did you correct it? You told me 5 milliohms.
Oh, I did not take the.
Oh yeah, okay. So you corrected it in your head, as always.
No,
That's wonderful. You see, now I've proven right. QED, wonderful to write, not just to use your head. Look, of course, use your head, right? Hence, the force on the wire will be 10 millinewtons. All right. Now let's look at the magnetic flux. Faraday found that a current was induced when an amount of magnetic field is passing through a coil or a loop, but not just that it passes through, that it's changing as it passes through that coil, right? If it's fixed and the magnetic field was fixed, nothing was happening. But when I move that coil in and out of a magnetic field, or I move the magnetic field in and out of that coil, it's the same situation. Then suddenly there seemed to be a current passing through it, okay? While motional EMF can be understood via magnetic forces on charges, this is not true for induced currents in general. We will need a new concept, that of magnetic flux through a loop, all right? All right, what does that mean? So, a magnetic flux, remember this from our Gauss discussion of electric field flux, right? We can also talk about magnetic field flux. So quickly, the question is, if I close and I make a closed surface and I calculate the magnetic flux, what should that number be? 0, because there are no magnetic monopoles. There's just no way to isolate a north from the south. However, if this area is not closed but open, I can calculate the flux through an area that's open. And that's what this expression refers to. I can calculate the flux of the magnetic field as long as that area is open. It's not a balloon. Okay? Oh, I wrote the answer. I asked the question. Sorry. Anyways. All right, so remember we have a wire, a loop, right? A wire that is in the shape of a loop. All right, so we can calculate the magnetic flux through this wire, okay, in the sense that this loop encloses an area, right? And as before, we defined the vector area as of size dA and its direction being perpendicular to the surface. And if you remember our discussion of electric field, there's still an ambiguity in terms of what the direction of N is. It could be pointing, as in this drawing, like that, or it could have been drawn pointing in the opposite direction. All right? So that is we need a way to figure out how we're going to draw this N uniquely. All right? So the way we uniquely define dA for this open surface is use a current. So the current is going around in this way, which for me would be counterclockwise, right? That then defines a direction through my thumb, right? And that is the direction of N. So that's how we uniquely define N. We define what's the direction of the current, and we define, therefore, N. If we didn't know the direction of the current, for whatever reason, which we might be in that situation shortly, like we do the Kirchhoff's laws, we assume a certain direction and a certain N, and of course if you get the current is negative, it was actually going in the opposite direction, right? All right, well. All right, so that's how we define N, by this right-hand corkscrew rule, all right? And our fingers are following the current, and our thumb is going to define that vector, which is perpendicular to the area enclosed by that circuit, by that loop. This is a simplified circuit, okay, and a loop. All right, and then with that we can then uniquely calculate the flux, all right? Where of course it's a dot product and it's B dot dA. That means that you're interested, the flux is really the part of the magnetic field that goes through the area, and anything that is parallel to the surface of the loop is not contributing to any flux. So if the area were, if this angle between N and B, right, was 180 degrees, 90 degrees, right? B dot dA is 0, which means that all the lines, none of the lines are crossing the area, they're just parallel to the surface of the loop, and therefore there's no flux. That's, mathematically you can get 0, but also visually, it's very important that you develop this visual aspect of the problems, okay? That helps a lot. In my experience, building that cartoon picture of what's happening is key to being a good physicist and then a good engineer, all right? Because you imagine the pieces coming together.
Yeah, although sadly that doesn't really work for quantum mechanics, does it?
It's counterintuitive, I agree, but you do really have to not think about it. What does it mean? So if you have a result, all right, and we can talk about experiments. Experiments in quantum mechanics, for example, show there were probabilities, that things were probable, that you could talk about things that would be probable. So for example, the best one that I have is what I do, which is I use neutrons and I scatter neutrons off of the samples I want to study, and they behave what we call as waves. These waves represent probabilities. And so if they go through and we're going to talk about that later in the last part of the course, if we have a beam of neutrons and they can go either through a hole on the right or through a hole in the left, what you get is a pattern on the other side that is a probability pattern. So having that intuition to build that physical image, Isaiah, that's what's going to happen, that is very important. So you can get an image of what quantum mechanics will do. Otherwise you couldn't even think of an experiment, right?
Right.
So yes, even in the very complicated case of quantum mechanics, we think about what that means in the physical world, all right? It's not just a simple equation that you learn in the classroom. It also has some physical significance, meaning when the angle is 90 degrees, the reason the flux is 0 is because at that point my loop is perfectly in a way so that the magnetic field lines are right parallel to the surface, and that's why the flux is 0, okay? Yes, the math is telling me that too, but visually I see it too. You see? All right. So, what you find is, well, we can calculate the magnetic flux. The magnetic flux in general would then, if the area is fixed, right? Meaning the area defined by the loop is fixed, the angle is fixed, and the magnetic field has a particular direction, that makes an angle theta with that vector n defining the area, then the flux is simply given by this expression. The units of the magnetic flux are called Webers. 1 Weber is 1 Tesla per meter squared, right? B dA, B is in Tesla, and area is in meters squared, so that's a Weber. All right, so the loop seen from the side, you can see that the magnetic field is parallel to N, so that actually means that the angle is 0 and the flux is maximum. As I start turning that loop, it starts to make an angle theta. The N starts to make an angle theta with B, and so the flux starts to decrease. Of course, when the theta becomes 90 degrees, the flux is 0. No? So this is another visual cue. you can interpret this as, if you're looking at the loop from this side, my eye is here, all right, my eye is here, I see the whole square, and therefore the maximum magnetic field through that loop. But if I put my eye here and it's turned, what I see is a loop that's much smaller, right? And so that's less flux. And that also has that image to it, okay? So let's do an example. At a particular location, the Earth's magnetic field is 50 microtesla, 10 to the minus 6, tipped at an angle of 60 degrees below the horizontal. All right, so the magnetic field, this would be parallel 60 degrees would be like that. All right, from the horizontal. A 10 centimeter diameter circular loop of wire sits flat on a table. All right, so its N, what angle is it making with the horizontal if it's flat on a table? The angle N, which is that of the loop, the area of the loop, what is the angle that it's making with the horizontal? 90. Exactly. What is the magnetic flux through the loop? The magnetic field is making an angle of 60 degrees below the horizontal. So what is the flux? Assume a particular direction of current. All right? Well, actually, decide what end you want. So the only difference between some guys will be a negative sign, because there's no current in this thing. So we cannot define N, so N will be undefined. So decide which N you want, and therefore what would be the flux. If you define it in a certain direction, the difference between, you might define it differently from him. What are the two options? Either it's flat and it's pointing up, or it's flat and it's pointing down. So the difference will be a sign. All right? That doesn't matter. So go. What is a flux? It's a loop that's whatever. Oh, right. Diameter. The diameter of the loop is 10 centimeters. That implies that it's a circle.